Hello, good morning. We can see your slides, but we can't hear you. Can you hear us? So you see, this is the problem on our side. We will solve it in a second. Thank you. So perhaps it's solved now.
Okay, can you hear me now?
Yes, we can. We can. So
okay, great. Yeah, there was a Zoom settings problem.
I'm ready. So good morning to you. Our next speaker is Laura Williams from Harvard University. And as you see, the topic of the presentation is the positive Grassmannian, the amplituhedron, and cluster algebra. So please, the screen is yours.
Okay, so thank you very much. It's a pleasure to be here virtually. I'll be telling you about work that's joint with various collaborators, including Stephen Harp, Tomek Lukowski, Matteo Parisi, Melissa Sherman-Bennett, and Yan Zhang. And so let me just start by giving an overview of what I'll speak about. I'm going to start by giving some background on the positive Grassmannian, and then I'm going to explain some background and motivation for an object called the amplituhedron, which was motivated by n equals 4 super Yang Mills scattering amplitudes. And I'll just tell you about some of the beautiful mathematical properties of the amplituhedron, including its connections to triangulations, cluster algebras, the positive tropical Grassmannian, and plane partitions. Okay, so now just some background on the Grassmannian and the Matroid stratification. So the Grassmannian GKN is the set of all k-dimensional subspaces of an n-dimensional vector space. And we like to represent elements of the Grassmannian by full rank matrices whose row span is the k-plane that we're talking about. And then let me just remind you the notation for Plücker coordinates. So if I is a k-element subset of the numbers 1 through n, then the Plücker coordinate P sub I of C is just the minor, the determinant of the k by k submatrix of C in column set I. So I've shown here a 2 by 4 matrix C, and then we have 6 different Plücker coordinates, and the set of Plücker coordinates give us an embedding of the Grassmannian into projective space. Now there's something called a matroid associated to each element of the Grassmannian or each full rank matrix. And for the purpose of this talk, I'm going to define the matroid of C to just be the collection of k element subsets of 1 through n where the Plücker coordinate P sub I is non-vanishing. And so in my little example, the Plücker coordinate P12 equals 1, and so the subset 1, 2 is one of my k element subsets in this collection. Okay, so back in '87, Gelfand, Goreski, McPherson, and Serganova studied what they called the matroid stratification of the Grassmannian. So this is a way of decomposing the Grassmannian into strata. And what we do is, if we're given script m, a collection of k element subsets of 1 through n, we let S of m be the set of elements in the Grassmannian where your Plücker coordinate P sub I is non-zero if and only if I comes from our collection. So that's the stratum S of m, and this gives a decomposition of the Grassmannian into these matroid strata. So we're really just decomposing the Grassmannian into pieces based on which Plücker coordinates are non-zero. So there's a lot of beautiful properties of the matroid stratification, but the topology of these strata is terrible. Benioff's universality theorem showed that basically the topology of these strata can be as bad as that of any algebraic variety. Okay, so that was the Grassmannian, and now I want to define the positive Grassmannian. And this goes back to work of Lustig in 94, Reach in 97, and Postnikov in 2006. And so one thing that comes out of these works is the notion of the totally non-negative or positive Grassmannian. And the positive Grassmannian is just defined to be the subset of the real Grassmannian where our Plücker coordinates are always non-negative. And if you're concerned about Plücker coordinates only being defined as coordinates in projective space, we'll just define the positive Grassmannian to be the subset of the Grassmannian where Plücker coordinates all have the same sign. Okay, and now inspired by this Matroid stratification, you could again partition the positive Grassmannian into pieces based on which Plücker coordinates are strictly positive and which are 0. And so again, if M is a collection of K element subsets of 1 through N, will let S sub M be the subset now of the positive Grassmannian, where your Plücker coordinate P sub I is strictly 0 if and only if I comes from your collection. And now in contrast to what we saw in the previous slide, where the Matroid strata had terrible topology, now when you look at these Matroid strata intersected with the positive Grassmannian, then you get actually cells. Your pieces are homeomorphic to open balls. And so this gives this positroid cell decomposition of the positive Grassmannian. And you could ask, so when is your stratum S sub M, when is it non-empty? Because of course, if you choose your collection M unluckily, then this S sub M may be empty. Okay, so now I'll describe when you get an actual cell as opposed to an empty set. And these cells can be understood very beautifully from certain bipartite graphs. So positroid cells correspond to what are called Platographs. These are planar graphs embedded in a disk. Boundary vertices are labeled 1 through N, and internal vertices are black or white. And without loss of generality, we can assume the graph is bipartite and that every boundary vertex is incident to a white vertex. And so now I want to explain how you can read off a positroid cell from such a graph. And we do that just using perfect matchings. So let's let M of G be boundary of P. So I'm going to define that in a moment, where P ranges over the almost perfect matchings of G. Okay, so let me, I have to define two things. I'll do it in this example. So first, an almost perfect matching of my graph G is a collection of edges of the graph such that every interior vertex, each black or white vertex, is incident to exactly one edge from my collection. So these orange edges show edges in almost perfect matchings. So this, for example, is an almost perfect matching because each interior vertex, white or black, touches exactly one orange edge. And we're saying almost perfect matching here because we don't care about whether boundary vertices get matched or not. And now if P is an almost perfect matching, then del of P is going to record which boundary vertices touch an orange edge. And so so these are my 5 almost perfect matchings of this graph here, and del of this almost perfect matching is just the subset 1 and 2, because 1 and 2 are the boundary vertices touching orange edges. Okay, so this is a way to start from a bipartite planar graph G, read off a collection of K element subsets of 1 through N. And the theorem is that this collection, M of G, is the set of non-zero Plücker coordinates of a positroid cell of the positive Grassmannian, and all cells are obtained this way. please interrupt if there's any questions. And so the positroid cells of the positive Grassmannian are in bijection with, so it's actually equivalence classes of these Platographs, which have also appeared in physics literature under the name on-shell graphs. And these cells are also in bijection with certain permutations. And so we can refer to cells as S pi, where pi is the permutation. And I'll just explain briefly how we can read off a permutation from one of these bipartite graphs. And it's a very easy sort of combinatorial game that goes through zigzag paths. So so this here is a Play-bit graph, a planar bicolored graph, and I'm going to show how to read off a permutation from it. So from every boundary vertex I, we're going to turn right when we see a black vertex and left when we see a white vertex. And that's going to give me a way of walking through the graph. So for example, if I start at 5, I go out, I see a white vertex, I turn left. Then I see this black vertex, I turn right. Now I see a white vertex, I turn left. I see black, I turn right. I see a white vertex, I turn left. See black, so I turn right, and then I go to 2. So I've taken a little trip in the graph from 5 to 2. And so that tells me to set pi of 5 to be equal to 2. And then there's 2 kinds of fixed points based on whether at your boundary vertex you see a little lollipop. Your path just sort of ends. I mean, I can view the path starting at 6 as going out to this white vertex, turning left and coming back to 6. And so in my example, I get this permutation here. And this is a permutation in one line notation, sending 1 to 8, 2 to 4, 3 to 5, and so on. And just to give one more example, how do we get the 1 to 8? We start at 1, we turn left at white, we turn right at black, turn left at white, turn right at black, and we go to 8. Okay, so this was the background, just that we have this object called the positive Grassmannian. It's a cell decomposition, it's a cell complex, and the cells can be beautifully indexed by some kinds of planar bicolored graphs, and they can also be indexed by some kind of permutations. Okay, so now I want to tell you about this object called the amplituhedron, and I'll just start by telling you where it came from or why. What was the motivation? So the motivation is coming from scattering amplitudes in n equals 4 super Yang mills. And the recurrence of Brito, Cacciazzo, Fang, and Witten expresses scattering amplitudes as sums of rational functions of momenta. And in this expression, individual terms have spurious poles, that is, singularities that are not actually present in the amplitude. And then Hodges observed that in some cases, this amplitude is actually the volume of a polytope, and that the BCFW recurrence can be viewed as cutting up the polytope into pieces, and those like triangulating the polytope, and then the spurious poles come from internal boundaries of that triangulation. And he asked if, in general, each amplitude is the volume of some geometric object. And that prompted Arkani Hamed and Trinka to find the amplituhedron as the answer to this question. And roughly speaking, the BCFW recurrence gets interpreted as giving a triangulation of the amplituhedron ANK4 of Z. Okay, so that is the backstory. That's where the amplituhedron came from. But now I want to define it mathematically. And the definition is very simple. It's just the image of the positive Grassmannian under a particular map. Okay, so here's the definition. We're going to fix positive numbers n, k, and m with k plus m at most n. There's going to be an amplituhedron for each triple of numbers. And in addition, we also fix a matrix Z. This is encoding external data. And Z is a n by k plus m matrix whose maximal minors are strictly positive. Okay, and now we're going to define a map Z tilde. It's going to be a map from the positive Grassmannian of k planes in n space to a related Grassmannian of k planes in k plus m space. And this map is simply induced by matrix multiplication. So if I have an element in this positive Grassmannian, GKN, that element can be represented by a k by n matrix C. And I just take C, I multiply it by Z. I now have a k by k plus m matrix. It's a lemma to check that it has full rank. And so its span represents an element in the Grassmannian of k planes in k plus m space. So this is the map Z tilde. And now the amplituhedron is just the image of the positive Grassmannian under this map Z tilde. So this is a subset of the Grassmannian of k planes in k plus m space. Okay, so at first glance, it feels like kind of a weird map. And I didn't know what to make of it when I first saw the definition, but this object turns out to have many beautiful properties. So first, I'll just mention the amplituhedron got quite a lot of press when it came out. It's featured in Wired magazine, Discover magazine, and Time magazine, one of the 25 best inventions of the year 2013. All right, so back to the amplituhedron. Let me just make a few remarks. One is that this amplituhedron makes sense for any m. Now, special cases include the m equals 4 amplituhedron, ANK4. And this is the object that encodes the geometry of tree-level scattering amplitudes and planar n equals 4 super Yang-Mills. Now the m equals 2 amplituhedron is also interesting. It's considered a toy model for the m equals 4 case, but it also has its own applications to physics. And yes, it's relevant to the MHV sector of the theory and the next to MHV sector. And okay, so several cases have to do with physics, but the amplituhedron makes sense for any m. Okay, so now I've defined the object, but let me show you a few examples so that you get a better sense of what kind of an object this is. So first, as a sort of silly special case, if m is n minus k, then this matrix Z is just a square matrix, invertible. And so the amplituhedron really just recovers the positive Grassmannian. So you can think of the amplituhedron as a generalization of the positive Grassmannian. Now, more interestingly, let's look at the k equals 1 and m equals 2 example. And the statement is that in this case, the amplituhedron, which is a subset of the Grassmannian of 1 planes in 3 space, is equivalent to a convex polygon in Rp2. So I'll just briefly explain why that's the case. So let's take our given matrix Z. This is an n by 3 matrix with positive maximal minors, and I'll label its rows Z1 through Zn. So these are they're row vectors in R3, which we can think of as points in P2. And the fact that our maximal minors of this matrix are positive imply that these points Z1 through Zn correspond to vertices of a polygon in Rp2. And then the map Z tilde is a map from positive G1n to G13, and it just sends our matrix, which in this case is a vector C1 through Cn, to this linear combination of CIs. And as the CIs range over non-negative reals, we get all points of this polygon. Okay, so that's why when K is 1 and M is 2, the amplituhedron is just a convex polygon in RP2. And more generally, if K is 1 and M is general, one gets what's called a cyclic polytope in projective space. Okay. Another nice example is that if M is 1, then the amplituhedron is homeomorphic to the bounded complex of a cyclic hyperplane arrangement of n hyperplanes. And so these are a couple of pictures of what it looks like in this M is 1 case. Okay, so now let me turn to the question of how can we understand the amplituhedron? And so I have just a review of the definition up here. So the amplituhedron, recall, is defined as the image of the positive Grassmannian under the map C tilde. It's a subset of the Grassmannian of K-planes and K plus M space, and it has full dimension. So the amplituhedron dimension is K times M. And now we understand the positive Grassmannian very well. It's this nice cell complex. And the positive Grassmannian surjects onto the amplituhedron. So we want to understand the amplituhedron using images of cells of the positive Grassmannian. And so some natural questions one can ask is, when is the map Z tilde injective on a cell S pi? And it's particularly interesting, so given that the amplituhedron has dimension K times M, it's particularly interesting to study the Km dimensional cells of the positive Grassmannian and figuring out which ones map injectively onto the amplituhedron. So if the dimension of a cell is Km and Z tilde is injective, then we call the image of that cell a tile of the amplituhedron. And so a question which goes back to the origins of the amplituhedron is, can you find a collection of these tiles? Can you find a collection of images of cells which fit together to tile the amplituhedron? Like in a non-overlap, we want to cover the amplituhedron in a non-overlapping way. Other questions are, how many tiles comprise a tiling? Can we understand all of them? Can we understand the amplituhedron directly inside the Grassmannian? And is there a connection to cluster algebras? So there's a cluster structure on the Grassmannian and various subvarieties of it. So it's natural to ask about this question for the amplituhedron as well. Okay, and we understand the situation very well when K is 1, which is the bounded polytope case. We also understand it very well when M is 1. And recently we've gotten a good understanding of most of these questions when M is 2. Okay, so let me tell you about some of the structural properties that we know when M is 2. Okay, so recall that we define a tile for the amplituhedron to be the closure of the image of a cell in the positive Grassmannian whenever Z tilde is injective on that cell and it has the right dimension, like it has dimension K times M, which is the dimension of the amplituhedron. So Lukowski, Parisi, Spradlin, and Volovich had given a conjectural characterization of all of these tiles, which we proved with Parisi and Sherman Bennett. And they have a very pretty description. So these positroid tiles are in bijection with collections of non-overlapping gray polygons in an n-gon with total area K. So here's my picture. So this, so here n is 9. We're looking at a 9gon. And I have here a collection of several gray polygons. And if I were to triangulate these gray polygons without introducing extra vertices, then this gray polygon is a quadrilateral. I would get 2 triangles there. And then this gray polygon is a 5gon, so I would get 3 triangles there. And so I would say that 2 plus 3 equals 5 is the area of this non-overlapping gray polygons. And such a picture gives rise to a tile as follows. So I'm going to triangulate my gray polygon into those k gray triangles, however I like. Put a white vertex in every gray triangle connected to the 3 vertices of the triangle. And then I can write down elements of a cell S pi, and these are going to be the k by n Castelli matrices with rows and columns indexed by the white and black vertices. So, so k here is 5, so I have a 5 by 9 matrix, and the different rows correspond to my different triangles in this picture. So I have a triangle here with vertices 7, 8, 9, and that gives rise to this row, which has stars in positions 7, 8, 9. And so basically, if I allow the stars in this matrix to range over non-zero real numbers with the appropriate sign, I will get a point. I will get all points in a cell of the positive Grassmannian, and that cell maps injectively to the amplituhedron. And all cells appear this way. Okay. So anyway, so in this case, we can understand very well precisely which cells map injectively to the amplituhedron under this map. So now I'll say a little bit about cluster algebras. Probably people have some familiarity, but they're a class of commutative rings with some remarkable combinatorial structure. There's a geometric analog of them called cluster varieties. These are varieties whose coordinate rings are cluster algebras. They come with many nice forest charts. And it's useful to find cluster structures because of the many general results about them. And so one question was, is there some kind of cluster structure lurking in the amplituhedron? And there were some clues from physics that the answer should be yes. Some various people had observed that when one calculates scattering amplitudes as rational functions of momenta, the poles arising in expressions seem to be related to compatible collections of cluster variables. And in physics, this had been referred to as cluster adjacency. Okay, but before I can tell you anything about cluster structures, I need to tell you about coordinates, nice coordinates we can use for the amplituhedron. So recall the amplituhedron is the image of the positive Grassmannian, and it sits inside the Grassmannian of k-planes and k plus m space. And we would like some coordinates that we can use to describe the amplituhedron directly inside this Grassmannian, instead of just thinking of it as the image of something else. Okay, so let's let Z1 through Zn be rows of the matrix Z. And then we'll look at Y, which is in the Grassmannian of k-planes and k plus m space, viewed as a matrix. And now if I is an m element subset of 1 through n, then I will define bracket YZI to be the determinant of the following matrix. So I'm going to take my matrix Y from the Grassmannian of k-planes and k plus m space, so that's k by k plus m, and then I'm going to stick below it rows of my matrix, particular rows, my rows Zi1 through Zim, where I1 through Im comes from this collection. And now I have a k plus m by k plus m matrix, so I can take the determinant. So this is going to be a coordinate that I can use for the amplituhedron, and we'll call these twistor coordinates. And actually, these twistor coordinates are really just Plücker coordinates in disguise. Okay, so anyway, so we have these coordinates for viewing the amplituhedron inside the Grassmannian where it lives. Okay, so I mentioned that for the m=2 Grassmannian, we have a complete classification. m=2 amplituhedron, we have a classification of the tiles. And it turns out that there's a cluster structure on each one of these tiles. And our cluster coordinates are exactly plus or minus the twistor coordinates y, z, z, b, where AB is a diagonal or an edge of a gray polygon. Okay, so if you've seen the cluster structure on the Grassmannian before, then this will probably be reminiscent of things you've seen for G2M. I'll just mention that twistor coordinates can also be used to provide a concrete inequality description of all these tiles and a description of the amplituhedron directly as a subset of the Grassmannian of K planes in K+2 space. Okay. So I've told you about positroid tiles for the amplituhedron, these images of Km dimensional cells where Z tilde is injective. But now we want to know, can we fit tiles together to, in a non-overlapping way, to tile or triangulate the amplituhedron? And so let me just make that definition a little more precise. So we'll say that a Z-induced tiling or a positroid tiling of the amplituhedron is a collection of closures of images of Km dimensional cells such that Z tilde is injective on each cell. And the union of these tiles is the amplituhedron, and the interiors are pairwise disjoint. Okay. And so when they introduced the amplituhedron, Arcani, Hamid, and Trinka conjectured that certain BCFW tiles give a tiling of the amplituhedron, and this was subsequently proved in a beautiful paper of Evans, Zohar, Leclerc, and Pessler for one instance of a particular tiling. Okay. So let's see. So again, some of the questions that we'd like to understand is can we classify all of our tilings? And in general, for general M, these questions seem very hard at the moment. But for m=2, we can classify all of the tilings. And the surprise for us is that this classification of tilings is very closely related to the moment map for the Grassmannian and the positive tropical Grassmannian. Okay, so I'm going to tell you now how the amplituhedron for m=2 and the amplituhedron map and pilings are related to the moment map. Okay, all right, so let's let E1 through En be a basis of Rn. And now if I is a subset of 1 through n, E sub I will be a 0, 1 vector indexed by I. This lies inside Rn. And then the moment map for the Grassmannian is just defined as follows. So if C is a matrix representing a point in GKN, then mu of C is this sum of E sub i's, these are 0, 1 vectors, weighted by squares of Plücker coordinates. And then we just divide everything by this normalization, which is the sum of the squares of the Plücker coordinates. So mu of C will be some point in Rn. If one looks at the moment map image of the whole Grassmannian, you get an n-1 dimensional polytope in Rn, which is called the hypersimplex delta Kn. And this is the convex hull of all of the E sub i's, where I is a K element subset of 1 through n. So if we draw delta 2, 4, well, this is a 3-dimensional polytope in R4, and it just has the combinatorics of an octahedron. So the vertices are all 0, 1 vectors where exactly 2 of the 4 coordinates are ones. Okay. Okay, so now, so recall that a matroid is a particular collection of k element subsets of 1 through n. And given that collection, we have a matroid stratum, which is a set of points in the Grassmannian with the corresponding Plücker coordinates non-zero. And we also have a matroid polytope, which is the convex hull of all of those E sub i's. And now Gelfand, Goreski, McPherson, and Serganova used the convexity theorem to show that the closure of the image of a matroid stratum under the moment map is exactly this matroid polytope. So if I'm ranging over points in the Grassmannian where these Plücker coordinates are non-zero, and I apply the moment map to all of those points and then take the closure, I'll get exactly this, this polytope. Okay, so that's a review of the moment map. And now what does all of that have to do with the amplituhedron? That's what I want to tell you. Okay, so this is just a summary of our 2 kind of geometric situations. We've got the hypersimplex, an n-1 dimensional polytope in Rn. It can be viewed as the image of the positive Grassmannian under the moment map. And we can look at what we would call tilings of the hypersimplex, which are ways of cutting up the hypersimplex into moment map images of positroid cells. And moment map images of cells are polytopes, matroid polytopes. So we're really cutting up the hypersimplex into certain matroid polytopes. Now, on the other hand, the amplituhedron, when m is 2, is a non-polytopal 2k dimensional subset of the Grassmannian of k-planes in k+2 space. Also the image of a positive Grassmannian under the amplituhedron map. And we can look at the tilings. Tiles will be certain 2k dimensional subsets of this Grassmannian. And what's very surprising is that tilings of the hypersimplex, delta k+1, n, and tilings of the amplituhedron for m equals 2 are related. They're in bijection. Okay. So this is just a careful definition of my tilings on both sides. On the hypersimplex side, my tilings consist of moment map images of positroid cells. And on the amplituhedron side, we're looking at Z tilde images of positroid cells. And we're in both sides, we're cutting them up into pieces, into disjoint unions of tiles. And then what we discovered with Lukaski and Parisi and proved with Parisi and Sherman-Bennett is that there's a bijection we call T-duality between cells of the positive Grassmannian of k+1 planes in n space and cells of the Grassmannian of k planes in n space, such that the moment map is injective on an n-1 dimensional cell S pi, if and only if Z tilde is injective on the corresponding 2k dimensional cell S pi half. So there's a bijection on the level of tiles, and there's also a bijection on the level of tilings. So a collection of moment map tiles gives a tiling of the hypersimplex, if and only if the corresponding tiles for the amplituhedron gives a tiling. So this is true for any k and any n, and I'll just show now the only example that we can draw, which is the following. So we have our moment map from G24 to the hypersimplex, which is an octahedron. And that gives rise to exactly 2 tilings of the hypersimplex, the octahedron. And I've shown, here's one tiling where we're cutting it sort of the octahedron kind of horizontally. And here's another tiling where we're cutting it vertically. And I've shown also exactly which cells have moment map images, the corresponding polytopes. And now on the other hand, I have the amplituhedron map from G14 to the amplituhedron. And this amplituhedron, since K is 1 and N is 4, is just a quadrilateral. And there are exactly 2 tilings of this quadrilateral, again shown in these pictures, together with the cells which map onto the tiles. And our theorem says that these tilings, the tilings for the hypersimplex, are in bijection with the tilings for the amplituhedron. And it's not too hard to look at this example and make a guess as to how one bijects the cells of the tilings. So the bijection is going to take this blue cell here to this blue cell here, this magenta cell here, to this magenta cell here, and so on. And if you stare at the permutations, you'll see that they're kind of related by a cyclic shift. So 3, 1, 4, 2, if we wrap around the numbers and start with a 2 instead, we get 2, 3, 1, 4. And this is the T-duality map on permutations, giving a map on cells. Okay, so the statement, again, which is true for any k and n, is that tilings of the hypersimplex are in bijection with tilings of the amplituhedron. Okay. This leads to a connection to the positive tropical Grassmannian, which is a kind of tropical analog of the positive Grassmannian. And I'll just sort of say in broad strokes what's happening. Points in the positive tropical Grassmannian are certain points in R to the n choose k. We can interpret them as height functions on the hypersimplex. And when we do so, that gives rise to regular positroid subdivisions of the hypersimplex. And now we have a bijection. So basically a point in the positive tropical Grassmannian gives rise to a subdivision of the hypersimplex. And then because we have a bijection between tilings of the hypersimplex and tilings of the amplituhedron, then we can use points in the tropical Grassmannian to construct tilings of the amplituhedron for m equals 2. And the sort of vague question is there some analog of this story when n is not 2? And yeah, we have no idea. Okay. So now let me just step back a little bit, talking about all m. So people have looked in special cases at tilings of the amplituhedron, and if you look at a tiling and just look how many tiles are in a tiling, that number is interesting. So when m is 1 or 2, you get a binomial coefficient. When m is 4, you get a Mariana number. When k is 1, you again get a binomial coefficient. And you can ask, what is the number for general k, n, and m that generalizes all the numbers in this table? And that number is the following. So let m of a, b, c be this triple product. Then we conjecture that a z-induced tiling of the amplituhedron for even m has cardinality. This number, m of k, comma, n minus k minus m, comma, m over 2. So this sort of crazy conjecture is consistent with everything we know or conjecture in small examples. And this number is of a lot of interest in combinatorics and other fields. You might be familiar with it. It counts non-crossing lattice paths, plane partitions, rhombic tilings, perfect matchings, and there's dozens of other interpretations as well. So I think it's very interesting that for some reason, the tilings of the amplituhedron seem to have cardinalities equal to number of plane partitions in a certain box. But so far, like for general K and M, we have no idea how to construct a tiling even conjecturally. Okay, so just to summarize, the amplituhedron includes a special case of positive Grassmannian, fixed polytopes, cyclic hyperplane arrangements, closely related to the hypersimplex on moment map. And it's useful to study the amplituhedron using the point of view of matroids, cluster algebras, tilings, and tropical geometry. And still many open questions. So thank you very much. And here are a few references.
Thank you very much for an interesting talk. And now we have time for 1 or 2 questions. Well, yeah, we have a question over there.
Any kind of similar story for, say, Lagrangian Grassmannians, or in other cases for homogeneous varieties? Or?
Yeah, that's a really good question. I think there's been a little bit of work maybe in the orthogonal Grassmannian case, but in general, not much has been done. I should say also there is a loop version of the amplituhedron, which is of interest in physics and has something to do with a certain partial flag variety. But in general, this has not been explored very much outside of the Grassmannian case.
Seems that we have no further questions, so please let us thank the speaker again. Thank you very much. And let's